So I started the recording now, so please continue.
Yes, thank you. So I'll be talking about some research that has been going on for the past, I don't know, 4 years. And it's about how to, basically the idea is how can we improve all these bounds for sizes of spherical codes or sphere packings, how can you make them better? And the idea is to use this thing called completely positive or copositive type functions to do it. David already had a talk about hierarchies, which is another approach which is actually related to this also. So I'm going to discuss a bit how these things are related, and each approach is more or less successful depending on the situation. Okay, so let me start. So the setup again is with independent sets. So you have a graph G, which is either finite or infinite. It doesn't matter. Of course, we are going to be talking mostly of infinite graphs. And an independent set, which we already saw the definition several times, like for instance in this Peterson graph here, is a set of vertices which does not contain an edge inside. So all the vertices are mutually non-adjacent, right? And then you can define, like for instance, these 4 vertices that I circled here in purple. And then the independence number of the graph, which is usually denoted by alpha of G, is the largest cardinality of an independent set. And then I write a supremum here, because when the graph is infinite, then maybe this number is also infinite. So it's the largest cardinality of an independent set. And that many of these problems, or all of these problems that we have seen this week, the sphere packing problem and spherical codes and all these problems, they can be modeled as independent set problems of graphs. So the first one is the one that I was very happy that Henry talked about, is the binary codes. So for binary codes, the vertex set of your graph is the Hamming cube, so the set of all 0, 1 strings of length n. And then you say that 2 vertices are adjacent, so 2 strings are adjacent if the Hamming distance between them is greater than 0, because you don't want the strings to be the same, so you don't want loops in your graph, and less than d, so less than the minimum distance of your code that you want. And then if you make this setup, then the independent sets of this graph, they correspond exactly to the binary codes of minimum distance d, right? Because if you have 2 vertices that are at distance less than d, then they are adjacent in the graph, and then they cannot be together in the independent set. And then immediately realize that the independence number of this graph is just the maximum size of a binary code, this parameter a and d. And there are several other problems. There is this problem that I like very much. It's called Witzenhausen's problem. And in this problem, the vertex set of your graph is the sphere in Rn, and 2 vertices are adjacent if the inner product, if they are orthogonal. So 2 points on the sphere, they are adjacent if they are orthogonal. So if the inner product is 0. In this case, independent sets, they are sets without orthogonal points, right? And you can have sets without orthogonal points that have infinitely many points. So any small enough spherical cap is such a set, right? So the independence number of your graph is infinite, which means that this independence number doesn't say much. So it is a meaningless parameter here. So then we redefine the independence number to something more meaningful. In this case, what we call the measurable independence number, which is the maximum, is the supremum of the measures of sets of independent sets which are measurable. So now you look only at measurable independent sets, and then you want to find what's the maximum measure that such a set can have. And the measure, of course, is the surface measure on the sphere. So there is this Witzenhausen's problem is determining what is this measurable independence number. And there is a nice conjecture by Gil-Kalai, which is the double cap conjecture, which says that the optimal solution, the best possible independent set, the largest one in this problem, is just two spherical caps and two antipodal spherical caps of radius pi over 4. They have to be open, right? So they are open spherical caps of radius pi over 4, and they are antipodal. So just like in the picture, the radius of this cap is pi over 4. The radius of this cap is pi over 4. So this is on the North Pole. This is the South Pole. And then you see there are no two orthogonal points that are two purple orthogonal points, two orthogonal points in my independent set. Because here inside there are no two orthogonal points, and the distance between here and here is actually pi over 2. So there are also not two orthogonal points. But this is a nice problem. It's called Witzenhausen's problem, and we don't know a proof of this conjecture, and we actually don't know the exact value of this alpha for every sphere except for the one-dimensional sphere. Okay, so other problems. So you have spherical codes. If you have the spherical codes problem, again, the vertex set is the sphere, and two vertices are adjacent. If they are close, if the angle between them is less than theta, which means that the inner product is greater than cosine of theta. And then the independent sets are now finite, and the independent sets, they correspond to spherical codes of minimum angle theta. And then the independence number of this graph is the maximum size of a spherical code of minimum angle theta. And finally, no, not finally, there are two more problems I want to discuss. There is the problem of one avoiding sets in Euclidean space. So here you have the vertex set is the Euclidean space, and 2 points that are adjacent if the distance between them is exactly 1. So this is a famous graph, right? So this is the unit distance graph of the Euclidean space. And there is a very old question about this graph, which was in the news recently because of some new developments, which is the Hadwiger-Nelson problem, which asks for the chromatic number of this graph. And this is actually related to the question that I posed here, which is what is the independence number of this graph? Of course, independent sets correspond to sets that avoid distance 1. We say that they don't include points at distance 1. And the independence number is actually infinite, because you can have sets of actually infinite measure that don't have points at distance 1. But then we redefine what the independence number is, and we make a measurable independence number, which in this case is just going to be the largest upper density of a measurable independent set. And in this case, the idea is how do you determine that? And again, this is only known for R1, right? So R1 in dimension 1 is the only case where we know exactly this number, which is, you can guess it is equal to 1/2. And in all other dimensions, we don't know this number, and we only have lower and upper bounds and asymptotic bounds. So we don't have any idea of what this number should be in all other dimensions. And finally, you have the sphere packing problem, where the vertex set of the graph is Rn, and two vertices are adjacent if they are close together. So if the distance is greater than 0, but less than 1, then the independent sets of this graph, they correspond to centers of packings, centers of the spheres in a packing of spheres of radius 1/2. Again, the independence number is infinite, but then you can redefine the independence number. You can say that the independence number has to be the largest density of the associated packing, or perhaps the center density of whatever you like. So then you have a workable, reasonable version of independence number, again, with which you can work. So I want to put this all in the same framework, and we are still figuring out actually what is the best way to do this. It would be nice to be able to treat these problems all in the same framework. And for now, we have some kind of meta theory for this. So these are different kinds of graphs, but they are all topological graphs, right? Because the vertex set is always a Hausdorff space. So let's say that you now consider graphs which have a Hausdorff space for the vertex set, and then you can put a measure on this Hausdorff space. You can put a Borel measure or whatever you want to measure the size of your independent set. And then you have two kinds of graphs that I showed you. You have graphs that I call locally independent, and they have the following property. Every compact independent set is a subset of an open independent set, right? So local independent graphs, I call them local independent because in particular, a single vertex is a compact set, and it has then to be contained in an open independent set, right? Because a single vertex is a compact independent set, and it is a subset of an open independent set. So in other words, every vertex of the graph has an independent neighborhood. And David was talking about topological packing graphs, which are somehow the complement of these local independent graphs, which is where every finite clique is a subset of an open clique. And in this case, of course, a single vertex is a finite clique. And then it has to be a subset of an open clique. So every vertex has a clique neighborhood, right? Every vertex has a neighborhood which is a clique. So in this sense, these things are complementary concepts. And then we can make a table. You have local independent graphs and you have topological packing graphs. And another thing that, and they are different, they are fundamentally different somehow. And then another thing that complicates or helps you is whether V is compact or non-compact. So if you have local independent graphs, so Witzenhausen's problem is an example of a local independent graph. And the binary codes are also local independent because it will just put a discrete topology. And the vertex set is compact because it's the sphere of or the Hamming cube. And the one avoiding sets in Euclidean space, the Hadwiger-Nelson related problem, is also locally independent, but it has a non-compact vertex set. On the other hand, spherical codes and binary codes are also examples of topological packing graphs with compact vertex set. And the sphere packing problem is an example of a topological packing graph with a non-compact vertex set. And there are many other problems you can put in this language also. For instance, you could ask for packings in a hyperbolic space, or distance avoiding sets in hyperbolic space, or projective space, or whatever you want. And then you are going to fit them in one of the cells of this table here. And you can imagine that I mean, between local independence and topological packing, it's not clear what is easier and what is harder. Sometimes one is easier than the other, but it's not so clear. But kind of it's clear that from compact to non-compact, the difficulty increases when you go to non-compact, right? So this is maybe the most challenging row of the table. Okay. So to attack all these problems in a single optimization framework, what we use is this amazing discovery, which is called the Lovász theta number. And Lovász introduced this thing in 1979, and people are still finding out everything that this parameter can do, right? So this paper of Lovász, I really recommend this paper. It's called On the Shannon Capacity of a Graph, and it's an amazing paper because it is the first time that I know of that, the first paper I know of where there is a proof of the duality theorem for semi-definite programming. It is one of the first applications of semi-definite programming before it was even known as a thing. It is a paper that is really, which is about the Shannon capacity. So it's really information theory, what he's doing there. So it's also related to codes, and it was not really known at the time exactly how it was related. So shortly afterwards, this was more clarified. It's a very nicely written paper. So it's really interesting to take a look at this paper. All right, so what is the Lovász theta number? There are several ways, and that's one of the nice things about it. You can give so many equivalent definitions of the Lovász theta number, right? I'm going to give definitions in terms of conic programming, which Frank was talking about in the beginning of the week. So I have a cone K of matrices, right? So this K is a cone of symmetric matrices. I will replace it then later by several possible cones. But for now, it's just a cone of symmetric matrices. And then I have a graph G. And this, for now, G is a finite graph, okay? So what is the problem? The problem is to maximize the trace inner product between the all ones matrix and A, right? So this is the same as the sum over all the entries of the matrix A. And you want the trace of the matrix A to be equal to 1. So you have a normalization condition. And you want A of A is a matrix which is indexed by the vertex set of your graph. So it's a real matrix, symmetric, indexed by the vertex set of your graph. And you want, when you have an edge of the graph, you want the corresponding entry of the matrix to be 0, right? So when you have an edge, the corresponding entry has to be 0. So this is the primal problem. And if you paid attention to Frank's lecture, you must be able, like within now, if you remember the table, you must be able within seconds now to give the dual problem to this problem. And the dual problem is as follows. I'm cheating a little bit here. So if you notice what I'm cheating about, then you can tell me later. But this is not that there is nothing wrong in what I'm writing here. So the dual problem is minimize lambda. Lambda is an upper bound on the diagonal entries of the matrix Z, right? And when you have a non-edge of the graph, but X and Y have to be different, but you have a non-edge, then the corresponding entry of Z has to be less or equal than 0. And when you have, and this matrix Z minus the all one matrix, it has to be in the dual cone of K, okay? So if you remember, the dual cone is the set of all matrices that are going to have non-negative inner product with the matrices in K, okay? So Z minus J has to be in the dual cone of K. Now we can try to replace K by several different cones and see what we get. So the first option, the first thing that you can replace K by is the cone of positive semi-definite matrices. So if you replace K by the cone of positive semi-definite matrices, you get the Lova's theta number. You get Lova's original parameter, right? The Lova's theta number. If you replace K by the intersection of the cone of positive semi-definite matrices with the cone of non-negative matrices, so you get non-negative positive semi-definite matrices, you get something called the theta prime number, which was later introduced independently by Schrijver and McAllis, Rumsey, and a third author I forgot. Then if you can replace K by two other cones, which are quite interesting actually. You can replace K by the cone of completely positive matrices, which is just the cone generated by external products, X transpose, where X now is not any vector, but a non-negative vector, right? So if you forget this part, if you forget that X has to be non-negative, then this is the cone of positive semi-definite matrices. But now if you say that you want to have non-negative vectors, then you get the cone of what we call completely positive matrices. And the dual cone of this cone is the cone of copositive matrices, which is the cone of matrices A, for which this binary form here is non-negative. So X transpose AX is greater or equal than 0 for every non-negative X, not for every X. So if you would say for every X, then you get the cone of positive semi-definite matrices. But I'm saying like now it only has to be true for X greater or equal than 0. Then you get the cone of copositive matrices. And the fourth cone you can put a cone of Boolean quadratic matrices, Boolean quadratic cone, which is the cone of generated by the external products X transpose. But now X is not only non-negative, but it's actually 0, 1. Okay, so now you have a cone which is actually a polyhedral cone because it is generated by finitely many 2 to the power cardinality of V vectors, right? So it's generated by finitely many vectors. It's a polyhedral cone. And the dual of this cone is, again, the set of all matrices for which X transpose AX is greater or equal than 0 every time X is a 0, 1 vector. And here you have the inclusion chain of these things. So the Boolean quadratic cone is a subset of the cone of completely positive matrices, which is a subset of, and a completely positive matrix is both positive semi-definite and non-negative. And such matrices are positive semi-definite. And positive semi-definite matrices are always a sum of a positive semi-definite matrix plus a non-negative matrix. And this is the dual cone of this cone. So that's what this means. It's just the dual of this. These matrices are always copositive. And copositive matrices are always BQC stars. So they are always duals in the dual cone of the Boolean quadratic cone. So the cone of copositive matrices is the dual cone of the cone of completely positive matrices. And the cone of the Boolean quadratic cone dual is the dual of the Boolean quadratic cone. And then you can prove many things. For instance, you can prove, the first theorem you can prove is that when you put this cone here, when you consider the parameter theta of G with the Boolean quadratic cone, which is the most restricted cone in this chain, you get an upper bound for the independence number. And in particular, this means that if you put any of these other cones here, if you put any of the other cones, you will also get an upper bound because you are only increasing the size of your feasible region, right? So you are having more and more possible feasible solutions when you put a larger cone here. So any of these cones is going to give you an upper bound on the independence number. The proof of this is very simple. If you take any independent set, which is non-empty, you can make a feasible solution, right? You just make A, which is the solution, is equal to chi I times chi I transpose divided by the cardinality of I. So if you look at what this means, is that A of xy is going to be equal to 1 over the cardinality of I if x and y are in the independent set, and 0 otherwise. So if you check now, the trace of this matrix is 1, and if you have an edge xy, then x and y cannot both be in the independent set. So A of xy is going to be 0. And if you just compute what is the objective value of the solution, so in a product between J and A, you get exactly I squared divided by I, which is I. So this is a feasible solution which has in the objective value as large as the cardinality of your independent set, which means that the theta number is at least the independence number, because I just took a generic independent set. So if I take the maximum, it's going to be also there. Okay, this is a very nice thing. This is a proof that actually Lovas did in his paper. It's not the main part of the paper, of course. It's a very simple thing. A more interesting thing is this: if you put here the cone of completely positive matrices, you get the independence number exactly. And this is a result that goes back to Motzkin and Strauss, I think in the 70s or late 60s. And it's completely in another language in their paper, of course. And then it was rediscovered by Etienne de Klerk and Dima Pasechnik more recently. I mean, not rediscovered, but they translated what Motzkin and Strauss did into this setting. So we already showed this direction of the inequality, that this is greater or equal than alpha. So let's show the other direction. And you are going to see, it's a very short proof that doesn't have anything really complicated. So let's take a feasible solution of this theta number problem here. So you take a completely positive matrix which has trace 1 and zeros at the correct entries, which are the edges, right? And let's derive from this matrix an independent set, which is going to have at least the cardinality of this independent set is going to be at least the objective value of this solution. So how do you do that? You know that this matrix is in the completely positive cone. So you can write it as a conic combination of external products of non-negative vectors. So it's alpha 1, F1, F1 transpose, alpha k, Fk, Fk transpose. So it's a conic combination, right? And I assume here that these vectors, they have Euclidean norm 1, because if they don't, then you can just rescale the alphas and you can make them have Euclidean norm 1, right? So since I get them to have Euclidean norm 1, each of these matrices here has trace 1. So the trace of A is just equal to the sum of the alpha i's, right? So alpha 1 plus alpha k is equal to the trace of A, which is equal to 1. This means that JA, which is the objective value of my solution, is actually a conic combination of the objective values of each of these matrices here, right? So JA is equal to alpha 1, JF1, F1 transpose, plus alpha K, JFK, FK transpose. And therefore, since JA is a convex combination of these things, it has to be less or equal than at least one of them. Because if it would be, of course, greater than all of them, then it couldn't, you would get a problem because you have a convex combination, right? It cannot happen. All right, so let's assume that that JA is actually upper bounded by J of F1, J times F1, F1 transpose. All right, so now let me say that I is the support of the vector F1. So it's the vertices for which F1 is positive, non-zero. Okay, so of course I call this I, so this is what's going to be the independent set. So why is this the independent set? Why is I an independent set? Because all these functions, they are non-negative, and all the alphas are non-negative, and this A is 0 when you have an edge. So if you have a pair of vertices here which is adjacent, then you are going to have a non-zero, a positive number for some entry corresponding to an edge, and you cannot cancel this positive number out with the other factors, right? So you would end up having a positive entry for an edge, which you cannot have. So that's why the support of I is actually an independent set. And then if you just do a very simple calculation, so JA is less or equal than JF1, F1 transpose, and now J is the characteristic vector of the vertex set times the characteristic vector of the vertex set transpose, and so on. If you just make a very easy calculation now and use the Cauchy-Schwarz inequality here, you get that JA is less or equal than the cardinality of I, which means that whatever solution you get of this problem, you get an independent set which has cardinality at least as the objective value of this solution, which proves the reverse inequality here, that theta is less or equal than alpha. Okay, so that's the very short proof of this fact. And for finite graphs, of course. And it shows it shows a few things, right? It shows that first that if you put a Boolean quadratic cone, you get exactly the same as if you put a completely positive cone, which is the independence number. It shows that these cones are NP hard. They are hard cones. Well, doesn't mean anything to say that they are NP hard, but optimizing over them, separation over them, membership, these are all NP hard problems. So these cones are intrinsically hard cones in contrast to the cone of positive semi-definite matrices, which is an easy cone, right? So you can separate, you can optimize over this cone. So these cones are not easy to deal with. And that's of course a price to pay because they are very powerful. So they allow you to they allow you to model an NP hard problem, which is the independence number problem. And by duality, you get the duo of these cones. So copositive matrices or BQC star are also hard cones, okay? But not everything, so the story doesn't end here, because even though these things are NP hard, you can try to find nice matrices that are going to give you constraints that you can use to improve your Lovász theta number. So you can write the Lovász theta number problem with a positive semi-definite matrix and zeros in the right places and trace is equal to 1. So this problem is easy to solve. And now if you are clever, you can try to find, in a clever way, you can try to find say, copositive matrices, right? A collection of copositive matrices that's going to give you a bunch of linear inequalities that's going to improve your bound, right? And of course, you know that if you add all possible inequalities, so if you add all these things for all copositive matrices, you get the independence number, and you don't have hope to do that. But maybe you can have a heuristic that's going to find you good copositive matrices that are going to give you good violated inequalities, and then you can improve your number. And that's what we try to do. And the idea here is really not to try to, you can try to do it by hand, you can try to be clever and find out nice matrices by hand. But what we do rather is we try to make this automatic. So we try to find an automatic heuristic that's going to find you nice matrices to add as constraints. But we try to do that not for finite graphs, which is a bit boring perhaps, but for infinite graphs, for graphs that are related to packings or the Witzenhausen problem and all these things. And I'm going to use the rest of my time to talk about these extensions. So quickly, I'm going to talk about extensions first to compact spaces. So now we have V as the Hausdorff space, and it's a Hausdorff compact space. And you have a finite Borel measure on V, which satisfies perhaps a few other properties, which I'm not going to mention here, but nothing very, very bad. And then you can come up with a cone of completely positive kernels or operators on this space, which is just a cone generated by all the kernels which are of the form F tensor F star, where F is a non-negative L2 function. Okay, so this is just a kernel that at X and Y is equal to Fx Fy. So this is the same as the external product of two vectors. And then you have the cone of, and then you take a closure, right? This is maybe not closed, so you take a closure in the L2 norm, say. And then you have the cone of copositive operators or copositive kernels, which is the dual of this cone, which is the cone of all kernels, symmetric, I forgot to write here, all symmetric kernels, which when you integrate against a non-negative function, gives you a non-negative number. So the double integral axy fx fy gives you a non-negative number. So this is the equivalent of x transpose ax for a finite matrix, right? Okay. So for a topological packing graph, Dobre, Dürr, Frick, and Valentin, they managed to show that this extension of the Lovász theta number gives you exactly the independence number of the topological packing graph. So in particular, we have an exact formulation for the independence number for the size of a spherical code, and it's as follows. So Z is a continuous kernel, so it's a continuous function with domain V times V, and it is symmetric. I forgot to write this has to be symmetric. So it's a continuous symmetric kernel, and Z has to be less or equal than lambda in the diagonal. And when you have a known edge, Z has to be less or equal than 0, and Z minus J has to be copositive when J is the constant to one kernel, right? So this is really like, look how much this looks like to the Lovász theta number for finite graphs. I only replaced matrices by continuous functions, okay? And I replaced the cone of copositive matrices. I replaced it by the cone of copositive kernels. Okay, so if you use the cone, if instead of the cone of copositive kernels, you use the cone of positive type kernels, so just the double integral is greater or equal than 0 for every f, then you get exactly the LP bound of Goethals, Dosart, Goethals, and Seidel, right? And all the improvements on the linear programming bound, be it like Musing's improvement, or Florian Pfänder also had an improvement, that extra inequalities you add to the linear programming bounds to get better bounds. So also Frank and Christine Bashok, they have the SDP bound, the 3-point bound. All these things, they are actually, you can also interpret them as adding a few, as just using a proper subset of this cone of copositive matrices. So you escape from the positive type kernels, but you go a little further to copositive kernels. So all these things, you can interpret them like that, even the hierarchies. And you can also do the same for locally independent graphs. The proof is quite much more involved than for topological packing graphs. And it's by Descartes and myself and Frank Valentin. And again, the problem is very similar to the finite graphs, but you get now the primal version of the lowest theta number. So you have A is a cone of completely positive functions. It's a continuous kernel. It is 0 when you have an edge, and the trace is equal to 1. And you want to maximize the double integral of this kernel. So again, you have an exact formulation for the independence number of a locally independent graph using these completely positive kernels. And this is not only like a curiosity. I mean, this is not only like a theoretical result. First off, you can use this to give, to improve bounds for these things, like for Witzenhausen's problem or for one avoiding sets. You can make much better bounds using these completely positive matrices, and in an automatic way, like you have like some automatized heuristic who tries to improve your bounds. And not only that, but you can also use this, a nice thing about these cones. I mean, that you say like, okay, so they are complicated NP-hard cones. Why are they at all interesting, right? So Etienne de Klerk, who is the guy who came up with this, one of the pioneers of these copositive cones and completely positive cones, he told me that one of his ideas was that if you use this, if you do it like that, then you hide all the ugly stuff of your problem. You hide them inside of this cone, right? That's why it's so powerful, because it is complicated. On the other hand, it's a convex object. So you get a convex optimization problem, and then you have a strong duality. And maybe you can use it for something. And indeed you can, because when you have like this infinite problems, for instance, you can get things like exact asymptotic bounds for the growth of distance avoiding sets by using duality, a strong duality. So that's a very, very nice application of duality in conic programming to a very complicated geometric problem. So to finish, I want to talk about how do you extend this actually to Rn? So that's a non-compact space. What do you do there? And that's very interesting, because it gives you a stronger version of the cone-Elkies bound. So say you have the cone, you have this cone everybody knows. This is the cone of positive type functions. So you have continuous functions from Rn to R. And if you look at any finite set of points in Rn, and you make this matrix fx minus y, where x and y, they run over this finite set, then this is a positive semi-definite matrix, right? So these functions are called positive type functions. And we know them. We know them because a Schwartz function is positive type if and only if it has a non-negative Fourier transform. And more generally, there is this thing called Bochner's theorem, right? That says that positive type functions are actually the Fourier transforms of non-negative measures, or measures, right? So we know exactly these functions. We have a nice characterization of them via Bochner's theorem. And then we can define copositive functions, right? What is the cone of copositive functions? It is the same, but instead of saying that every finite submatrix has to be positive semi-definite, now it has to be copositive, right? Then you get a super cone, you get a larger cone than the cone of positive type functions. Okay, so for this cone, as you imagine, we don't have such a nice neat characterization because it is a much more complicated cone. But we can use it to give the following theorem, which is by David Delat and me. You have an optimization problem. So you are trying to compute the infimum of f0 plus g0. F hat of 0 is 1. F of x plus g of x is less or equal than 0 if x has norm at least 1. And f is a positive type function, and g is a copositive type function. And they are both admissible. And I'm going to say what admissible is. And the theorem says that actually, if you compute this infimum, you get exactly the sphere packing density, which I'm calling delta n here. I think with this normalization, it's the center density, right? Okay, so what is admissible? Admissible can be one of three things: either bounded supports, and then this makes this theorem a bit easier to prove, or it can be L1, which is then you just reduce this case to bounded support, or it can be a Schwartz function. And then the proof of this theorem is harder. So we are saying that if you find Schwartz functions that are positive type and copositive type, and they satisfy these constraints, which look exactly like the linear programming bound constraints, then you can get exactly the sphere packing density. So the Kohn-Elkis bound comes from this thing by just setting G to be the zero function. So you forget about the copositive function. So you lose this extra freedom you have here, and then you get an upper bound, right? And then you can also, it's a nice exercise to prove that the sphere packing density is less or equal than this infimum, because the proof is the same as the Kohn-Elkis bound proof. Okay, so this is saying that, I can use a function here to help myself become negative when I have to be negative. And then I have to pay the price. I have to pay a bit for it. But maybe I can find a clever function, or the theorem says you can find a clever function that's going to give you get you as close to the optimal, to the sphere packing density as possible. It's just maybe very hard to do, right? But maybe you are clever and you can find a function you can put here, a function that's going to help you a little bit, maybe not all the way, but a little bit. And that's actually something that we did, I think 2012 or so, but it was not in this language. I'm going to show you a copositive function. So imagine that you have a central sphere of radius a half, and then you have spheres of radius a half that are non-overlapping, and they are the centers of these spheres. They lie at distance between 1 and 1 plus epsilon, whatever epsilon is a very small number, from the center, right? So how many such spheres can you place in this strip that are non-overlapping and don't overlap the central sphere either? So this number is alpha, right? So this alpha is going to be an upper bound on this maximum. And then the following radial function is actually copositive type. You just set G to be equal to alpha for all the distances from 0 to 1, and then equal to -1 from 1 to 1 plus epsilon, okay? And then 0 everywhere else. So this is your function G. And this function is copositive. It's actually non-trivial to prove it. This function is copositive. And the nice thing about this function, it leads to the only known. I don't know if there are other improvements actually, but as far as I know, this function, or functions like this, they lead to the only known improvement of the Kohn-Elkis bound that we know, right? So for small dimensions, this is the only known improvement that we know. And then we are trying hard. I didn't give up 100% yet, but it's harder than the other cases. We are trying to find an automatic way to find such copositive functions that are going to really help you to get better bounds, improve the Kohn-Elkis bound. And I think this is possible. I think there is a lot of power in this approach. If you think of the Witzenhausen problem and so on, it was so powerful in that case. And here we know we can get an improvement. We just have to find a way to find a nice class of functions that are copositive that we can then use in the optimization. So that's the message of my talk. So I wanted to show you how you can actually put all these problems in the same framework and then look at them as optimization problems and just try to do what people in optimization do all the time, which is improve your numbers, right? I also hope these functions can be also useful in other contexts. So I'll be happy to know people that have problems that for which these can be helpful. So that's my talk. Thank you very much, and I'm open to questions.
Thank you very much, Fernando, for the nice talk. I just stopped the recording.